Oh, we're just about there. Welcome back, everyone. Well, welcome back. Looks like we can start officially. We're at the week of N9, so happy Thursday, everyone. And congratulations on getting through exam number 2. We're on our way through the course. My goal is to get these graded on Friday, but it could take a little bit longer. I'll try to get them graded as soon as possible. Hopefully sometime on Friday afternoon. If it goes a little bit later, I might be grading them Saturday morning. If it goes really late, they'll be graded on Sunday morning, but I try not to go that late. That kind of just eats out the weekend. Well, our other things going on is quiz number 6. This is on exponential growth decay, is due today. If you're prioritizing studying for exam 2 and you need a little bit additional time, no worries, accept full credit for these quizzes even if they go past due. Our new quiz number 7 is based off section 3.7 dealing with logarithms. So it's a really fast, quick tour on some of those kind of derivatives we took in that section. But for what we're doing today, we're now finally going into a new chapter. Chapter 3 was a pretty long one. And now chapter 4, we won't take as much time covering as many sections, but the major topics we're going to be looking into will be applications of the derivative. It starts off kind of slow with maximum and minimum values, but then it gets pretty interesting when we use all these concepts towards the goal of doing some optimizations in applied settings. Well, that's our goal so far. Any questions whatsoever, folks, to start us out today? Okay, well, let's jump in. It's a brand new chapter, so that's kind of exciting in its own sense. And here we're talking about first absolute maximum versus absolute minimum values. Then we'll look into local maximums and local minimum values, seeing how to spot the difference by doing all 4 concepts together on example 2. But then we'll see how the derivative plays its role in these kind of problems and start talking about, at the end of the notes, how to do a certain method that's going to find an absolute maximum and an absolute minimum to any random function we put down. So first thing you have to do is go through the initial definitions. And even though we all have a pretty good intuitive idea of what we mean when we say a maximum of a function or a minimum, these ideas can be kind of tricky sometimes. So example 1 is really 4 different kinds of functions, where we're going to spot what the difference will be if we change the domain in each one of these settings. So first, let's go through the original definition. We'll say f of c is an absolute maximum value of a function f on some domain D. It could be all real numbers, or a finite length set like this one, closed interval from 0 to 2. It's the absolute maximum if the function value at the input c is greater than or equal to f of x for all other inputs in that domain. Then likewise, we say the function value f at c is an absolute minimum if f of c is smaller than or equal to every other function value in that domain. And right away, one big takeaway here is whenever we say absolute maximum, or minimum, notice it's not talking about the input c. It's not the value x on the value on the x-axis. When it says f of c, it's the entire output. It's a value on the y-axis we're referring to. And that definitely will affect the notes, or the problems rather, when you're doing WebAssign. When you're putting an absolute maximum or minimum value, this is always a y-coordinate value, or the output of that function. So that's why we're calling it f of c, not c itself. So with those definitions in mind, here's 4 random functions. They all have the algebraic structure y equals x squared, but if you change the domain of a function, you've in fact changed the whole entire function. For this problem, we're going to state the absolute maximum a minimum of the function. And just for the sake of clarity on the instructions, I should have wrote, let's add a quick edit, if they exist. Not all functions will have an absolute maximum nor a maximum minimum necessarily. It just depends on the function and the domain of the function as well. So that's a quick edit just for the sake of clarity. And on our first run through on this one, we have the quadratic function y equals x squared. Well, we can say at least one thing looking at right away. That's the lowest value on the graph, 0. So it surely does have an absolute minimum. We can say for absolute minimum, I'll abbreviate that to ABS for absolute and MIM for minimum. It would be 0 on this graph. But what would you all say if you were asked, what is the absolute maximum? What's the best response on this one? Infinity is not a bad idea because, yeah, this graph just keeps on going up and up and up. So the concept of a maximum just seems kind of broken on this one. Saying infinity would be a way to say it doesn't actually reach a maximum whatsoever. At the moment you say any number whatsoever, like 10 to the power of a million, that's a humongous number, but then 10 to the power million plus 1 is in the range of this function. It just goes up without stopping. So for this particular problem, what we would typically say is absolute max. Let me change the color. Absolute max on this one, we would just say none. And that's what the homework exercises would be going for as well. You could say undefined, does not exist. But what we're looking for a true absolute maximum is a definite number. So if we can't put a number, we wouldn't even say infinity. We would just say none on this one. So there's nothing wrong with the function. It just happened to go up without bound on either side. And now this is what's going to happen when we just change the domain. We've restricted the domain on the second version here to just being from 0 to 2. There's kind of a shadow of what the original y equals x squared was on the entire real number line. But there's a hard cap right here to go with that interval being closed at the 2. There's a hard dot right here to go with that lower bound being 0. If we change that, the new thing that happens is, well, we still have the same absolute minimum. It's right here at height 0. But now it absolutely does have an absolute maximum as well. It's not 2, that's just the input. We're putting 2 inside the squaring function. It's outputting a value 4. And that's the largest function value that ever occurs. So we can say, I forgot to plug that in, 0 for absolute minimum. On this one, the absolute max is going to be equal to 4. So this one is on a closed interval. They had both an absolute maximum and an absolute minimum at the same exact time. But if your interval is all real numbers, well, it just depends on the function now, whether it will have both of them. It had a minimum, but not a maximum on this one. And it gets weirder still. This one was a fully closed interval. And this one is half open, half closed. Open on one side with the parenthesis, closed on the other side with the hard bracket. And just for the sake of curious out there, if it's half open and half closed, like in this one, this is a real mathematical word. This is sometimes called a Clopin interval. That sounds completely made up, but that's a real statement there. Just for novelty's sake, we'll use that language. So when we put a parenthesis on it, it caused an issue on the graph right there, an open circle. And we were looking at a lot of these kinds of issues when we were taking limits of functions, discussing continuity and so on. If you put an open circle there, well, let's focus on the good news. There'll still be an absolute maximum and still going to be the same value, 4. Absolute max is 4. But it actually got pretty weird on the absolute minimum. Much like how there's an issue here on the absolute maximum, something's going on with this one. Absolute minimum. What would you all say for the absolute minimum on this one? Exactly. The absolute minimum is none. And that's really surprising in a certain sense. So good call, none on this one. Let's put in an exclamation because in some sense, that feels probably kind of weird, right? But this is a side effect of having one side being open with a parenthesis. It has some weird behavior. Absolutely, Haley, this one wouldn't have a minimum at all. But it's kind of fun to think about this one. It sometimes can defy logic and reasoning why it has none. So imagine you found one. Let's say our function is f of x is x squared. This has a specific domain, so let's put that in. The domain is going to be 0 less than x, less than or equal to 2. So there's our whole function plotted, same as this one down below. And now if you found a value that you feel like is the minimum because it's really, really small, you would have to say what the input is, right? Maybe you put in 0.1, and that's your minimum. Except it's not a true minimum whatsoever. 0 isn't the actual minimum either, because notice you cannot put an actual 0 inside there. It's undefined. There's an open circle there. 0 is not part of the domain, so we can't compute f at 0. So you could put in a 0.01. That's quite small. For measurements around the house, if you're doing cabinetry work, that's pretty close to a 0 value in terms of centimeters, say. You get this value. But now, because that's an open interval, you can get as close to 0 as you would like. You just cannot hit 0. So put in another 0 there, and the height drops really, really low. It's going to use scientific notation eventually. But this game goes on forever. You can make the input value smaller and smaller. The output value keeps on dropping lower and lower and lower each time. And that means we never hit a minimum, because a minimum would be smaller than any function value for all x's in the domain. So if you said that's the minimum, someone can come up and say, well, what about f at 0.00001? That's even smaller. Following the order of magnitude, 10 power negative 10 is much smaller than that value there. So having an open interval makes things weird in that certain sense. If it's closed, it's no big deal. You can just put in 2, you get the 4, and you can never exceed this value 4 because you can't put in 2.1. It's leaving the domain so undefined. So the domain of the function is just as important as how the function is defined in the first place. And if you go to this one, 0, 2, a fully open interval, this one will have neither a minimum, let's say absolute minimum to tie together the full name of the concept. It has neither an absolute minimum nor an absolute max. Simply because 0 and 2 is not in the domain, and you get higher and higher and higher the closer and closer you get to 2, much like the issue here having no minimum whatsoever. So that's one normal function and 3 different pretty weird ones. Notice that this is a nice case. If you have a closed interval, you automatically will get an absolute minimum and an absolute maximum if your function's continuous. So we'll come back to that concept. But any questions at all, folks? Just working through these definitions. Okay, sometimes absolute maximums and absolute minimums are thought of as global maximums, global minimums. Same exact concept, just slightly different verbiage. Global in the sense that if it's a maximum, it beats out the function value, this one being the maximum, for all other x's in the domain. But going from absolute or global maximum and minimums, we can have a slightly different concept. The idea of local maximums and local minimums. Here's where we want to go really, really carefully, because at this stage, the definitions absolutely get tricky. So we still have a notion of what we mean by maximum and minimum. The definition says the number f of c, still a y-coordinate, just like on the last page, it's going to be a local maximum value of the function if it's larger than all other function values when x is near c. That's kind of a weird definition there. I mean, it's not even a true definition until we say exactly what we mean by near c. That's kind of a strange way to say this. So when we say something is true near a value c, we mean that you could put an open interval, much like the 0, 2 in the last example there. There's some open interval, let's call it AB, where c is on the inside. So if we say f of c is greater than or equal to f of x, when x is near c, we specifically mean for all x in an interval AB, it's open, so no brackets on either end, where c is in AB. It could be the direct center. It could be a little bit closer to A or a little bit closer to B, but it has to be somewhere between the range from A to B, just not on the endpoints. Because it's an open interval, it can't be equal to either A nor B at the same time. So that's our definition. Local maximum says just nearby C, locally, you placed an open interval around C, the function values exceed everything else. Likewise, minimum, we're saying if you're just near C, the function value f of c is less than or equal to everyone else, all the other function values f of x. So that's the definition so far. And in my opinion, this definition is tricky enough that let's open up a couple windows, maybe a file explorer. When you're doing these kind of problems, say on a quiz, maybe even on WebAssign, what you want are a couple blinders, maybe a couple just maybe your hands, something to cover up what you're seeing there, because this is tricky enough that sometimes you don't want to look at the whole graph to determine which one's the local maximum, which one's the local minimum. So this problem says, find both absolute and local maximum and minimum values of this function y equals g of x. We're going to discuss the caution as well once we get to this. Well, might as well discuss it right now. One caution that makes local maximums and local minimums even trickier is when we say local, we're talking about x near c, which implies we're talking about an open interval containing c at the same time. But that causes one side effect in that definition. We're going to take this definition as literally as possible. And when we do that, it implies there is never a local maximum nor minimum value at the endpoints of the domain of a function. And the reason for that is if we're at the endpoint of a domain of a function, you cannot fit an open interval inside the domain around that endpoint any longer. So we'll illustrate that as we get through this graph. The other thing that's equally tricky is absolute maximums and absolute minimums can occur on the endpoints, just never the local ones. Let's maybe highlight that right there. So that makes both sets of definitions, absolute versus local, exceedingly tricky. We're going to take our time on example 2 as opposed to example 1 and go through this set of all local maximums and all absolute maximums and their minimums. Okay, well, let's give this a try. I'm going to go left to right, and the graph is kind of annoying since I don't have all the values printed on. So let's put these in so we don't have to count them out each time. 1, 2, 3, 4, 5, 6. This goes off to 7 at the very end. I'll leave that off so it doesn't conflict with x. Then 2, 3, 4 goes to a height of 5 in the vertical direction. And the first interesting problem point is right here at the red dot. But based on what we did on example 1, nothing's happening here. This is neither a maximum nor minimum occurring at 0. So let's just put this down as a reminder. F at 0 is neither a max nor a min of any kind, neither local, maximum whatsoever. The moment you have an open circle, we lose all of that kind of information. No max or min there whatsoever. Then we go along the graph until we go here. Something interesting does happen at f at 2. Let's think about absolute maximums, minimums. This is not a maximum because other values are higher, so it can't be an absolute maximum. This can't be an absolute minimum because other values are even lower than f at 2. But in terms of local maximum, local minimum, looks like something is going on there. Anyone spot what's going on with this one? Is this a local max or local min? Yeah, good call, Haley. It's a local minimum right here. Now let's think about why it is, just working through the definition strictly, but f at 2, I'll give it the output as 2 as well. F at 2 equals 2 is a local minimum value. So focusing on that output for the local min, here's one way to think about it. First, let's just think purely geometrically, then we'll tie it in with the definition as well. It's not an absolute minimum like we discussed because other function values are smaller at height 1. But if you were to do this, put a hand over the graph like that, put maybe another hand or maybe a note card, something like that over the graph over here, notice that in this nearby region, locally around 2, or when x is near 2, the values are always higher until you hit 2 itself. So that's what this is saying. Function values are always higher until we plug a 2 in there, and we drop down to height 2. So this equation, this inequality rather, holds when x is near c, because you can put an open interval right around here. The interval might be, say, from 1.5 up to 2.5. Then from 1.5 to 2.5, that function value right here at height 2 becomes the minimum. If you extend too far, say if you went off to this domain from 1.5 to 4.5, this is no longer the smallest value whatsoever. So if we're covering up the graph and looking at it from this point of view, going from here way out to here, that's not a local minimum any longer, but that's okay. If we restrict the interval tighter and tighter until we're looking at this, if it becomes a minimum when we're just really close, very local, very close to 2, and this becomes the lowest value, then that's what makes it a local minimum altogether at that point. Well, that's one down. Any questions or comments on the f of 2? Okay, moving across the graph, if we go up to this one, here we have a horizontal tangent line, so the slope is 0 there, the derivative is 0 there. But also, if we're, say, using the note card trick and visualize the function this way, right around 3, that's a maximum value. So we have a local maximum at that location, and we can say f at 3. What does f at 3 equal to? It outputs a value 4, which tells us that 4 value is a local max. But notice something kind of curious happened at that local max as well. On that local max, f prime at 3, the derivative of f at 3, is immediately 0 because the tangent line is horizontal right at that spot. This is going to start to give us some indication in the later sections, including this section as well, of what to look for if you're trying to spot local minimums, local maximums. So we had derivative existing here. Then we come down to this sharp point right at 4. We can say f at 4 equals a value 1. But in view of both definitions, local maximums, local minimums, what would you call this one? Is this a local max min or is it an absolute max min? Any volunteers on how to categorize this one? That's true. This one would be a local minimum right here. And this is where it gets weirder still. It's a local minimum because you can put an open interval around it like this. And on a very short open interval containing 4, that's a minimum value. So we can call it a local minimum, and it's absolutely correct. However, at the same time, if we're looking at the entire landscape of the function, right at 4, that's the lowest point on the whole graph. 1 is the only spot it's ever occurs right at 4. So this one is both an absolute minimum and a local minimum at the same exact time. So these definitions get tricky in that sense. Things can be both locally an absolute maximum, and I said that weird. A value can be an absolute minimum, maximum, and at the same time, a local minimum or maximum, depending on where it occurred. So that's another one down, but this one gets weirder still because of that issue. The definition, again, still works if you're in an open interval around 4. That's the lowest point. But in terms of absolute minimums, it's also the lowest point on the entire graph. So it's also an absolute minimum at the same exact time. This graph just has lots of weird things going on with it. Well, any questions, folks, with that one there? Okay, now going beyond 4, we move upwards on the curve. It's increasing, transitions to decreasing around 6. Much like here it was decreasing, then transitions to increasing around 4, giving us both a local and absolute minimum. Here, we're looking at a local max. It's not absolute though, because there's other function values at a higher height than 3, certainly. The values get up to excluding 5. You can get as close to 5 as you would like. That means right here at 6, we have a local maximum. The local maximum is not 6 though, so let's emphasize f at the function input 6 gives the output the function value of 3, and this is a local max. So around 6, if all we care about is this part of the curve, just that small isolated area, right here, that's a peak, that's the highest point. So we call it a local maximum in that sense. Then when we move to the right, we hit a boundary point right here at the endpoint. It's absolutely, or I shouldn't say that, it's not an absolute minimum because that was the absolute minimum. It's not at height 1. But it's also not a local minimum because this is the endpoint of the domain of the function is right at 7. For it to be local, you have to fit an open interval a to b inside the domain. But the domain ends here, it can't be a local minimum either. So let's put down here, even though it's not a minimum maximum of any kind, it's still good to put on the notes. F at 7 is, let's give the output as well. F at 7, which is equal to 2, is not a local min because 7 is the endpoint of the domain. And right at the endpoint of the domain, there's no notion of nearby 7 any longer, because now we can't throw in an open interval that's containing 7 and still inside the domain. The interval would have to go to the right, just slightly beyond 7, but we've left the domain at that point. So these are, in my opinion, some really tricky concepts. Let's put here one more thing. We had a local max, and the derivative happened to be 0 here. We had a local max, and it could have been a local minimum, but in either case, the derivative, f prime at 6, was also 0 on this one. And there's some other weird things going on. Right at 2, we can say a little bit more about that one. F at 2, f prime at 2 does not exist. The reason derivative doesn't exist at 2 is it has to be continuous at 2 for the derivative to exist at the very first place. So the derivative didn't exist there whatsoever. But you know what? It also doesn't exist at 4 either. So f prime at 4 also does not exist. The reason it doesn't exist at 4 is the derivative fails to have a value whenever you have a sharp corner, or sometimes called a cusp. At a corner, or cusp, you could call it, f prime does not exist. Well, this is the conclusion of example 2, but any questions or comments at the moment? Okay, let's explore just a little bit more what I was saying on this concept here. I think this one is easier to see. The derivative doesn't exist at 2 because it's not continuous at 2. Differentiability implies continuity. So if we lost continuity, differentiability is completely off the table as well. But thinking about that corner once again, that's a little bit trickier to look into. So let's blow this up just a little bit more. Let's really look at what's happening at 1, 2, 3, 4 specifically. My claim was the derivative of f at 4, let's just say in ordinary English, does not exist. We also said that, let's maybe use about this color here. The derivative of f at 3 was 0. Likewise, if we put a horizontal tangent line through here, it has slope 0. F prime at 6 was 0. So the question now becomes, why can't we put a derivative value here at 4? But here's a thought that ties that together. The slope of the tangent line itself is telling you what the derivative is. That's how we knew the derivative is 0 right at 3. The horizontal tangent line, or excuse me, the tangent line is perfectly horizontal. So the slope is 0, and it gave us an immediate value. So what's going wrong at 4? If you put a tangent line, say here, at this point, really close to 4, it's about at, say, 3.8. A tangent line would look about like this. And the slope would be certainly negative, a pretty large negative value. So now if you're on the other end, say you're at, say, 4.1, you put a little dot here and put in a tangent line. Tangent line, that's not my best tangent line. Let me try again. The tangent line is going to look about like this now. But this time the slope is large positive this time. And it gets worse and worse the closer and closer you get to 4. If you're really, really close to 4, say 3.9999, or really close to 4 at say 4.0001, the slope to the left gets even larger positive, the slope to the right gets even larger negative. That means we have no sense of what the slope should be right at 4. This one has no value because small change to the left or small change to the right, and your slopes are totally different. The derivative isn't allowed to do that. The derivative itself has to be continuous for it to be defined. So that's why the derivative doesn't exist on 4 for this particular one. My computer's fan is spinning up really crazy. Sorry if you're hearing that on Zoom. But any questions at the moment, folks, with this graph here? Okay, so with our careful look at these problems with local minimums, local maximums, absolute minimums, absolute maximums, there's one big takeaway. Notice that every time we found a local minimum, local maximum, or in the case we found an absolute minimum, the derivative was either 0 or it did not exist. So we're going to use this information. We're going to look for maximums, minimums, whether they're local or absolute, of a function like g, but we may not always have its graph. Yeah, this graph is kind of telling us a story of where to start looking for trying to hunt for maximums and minimums. We should find where the derivative is 0. We should also find where the derivative doesn't exist, and that's our starting point. These aren't guarantees that lead to maximums or minimums. They're just where we begin to look. So putting this information together, we have 2 powerful theorems that are going to help us out: the extreme value theorem and Fermat's theorem. Not Fermat's last theorem, that one's kind of infamous, but this is just an ordinary theorem from Fermat. Fermat says, if f has a local maximum or minimum at a value c, and if the derivative exists, that derivative has to be a 0. That's what we were seeing in the last graph. And this one's more about absolute maximums and absolute minimums. I think we use these colors. The extreme value theorem says, if you have a continuous function, so continuity has to be on the table to use this function, and if continuity happens on a closed interval, bracket A, comma, bracket B, so including the endpoints, then, that's the 2 required ingredients in order to have a guarantee of the absolute maximum and the absolute minimum. If you look on example 1, the one graph that did have a closed interval, that's the one that had both the absolute max and the absolute minimum. So let's explore this theorem a little bit, then we'll look into Fermat's theorem to lead into next. So one way to think about the extreme value theorem, that's kind of a typical way to think about it, is strip away conditions and see what happens. We're told continuity and closed interval guarantee an absolute maximum, absolute minimum. So let's suppose we strip off continuity, keep the domain at closed interval, and just see what happens. So let's say it's defined on, let's make that interval a little bit more concrete. So let's make it a bracket 1 to 3, but not continuous. I'll use CONT for continuous as a shorthand. On a second version, we're going to look into what happens if we take off the closed interval condition. So strip that and say it's continuous. On an open interval instead from, let's make that 1, 3, just to match that up. So that'll be our second graph. Then our last graph, we're going to look into having both conditions. It's both continuous and continuous on the closed interval. So continuous on 1, 3. So here's three different kind of scenarios that can occur for some random function. The domain is going to be 1, 3, but it's going to change from an open set to a closed set on these two different panels. And it may be continuous or it may not be continuous. So let's first look into this situation. We're going to emphasize quadrant 1. So we're going from 1 to 3 here. We're defined on 1 to 3. So if we have a closed in set here, that means the function has to have a solid dot somewhere. Likewise, if it's closed on 3, f of 3 exists. It has to be somewhere, either above or below the x-axis. I'll put it below, why not? We have some space down below. So now, this might have an absolute maximum. It could have an absolute minimum, could have both. But there's no guarantee. The guarantee is only for both continuity and the closed interval. So if we take off continuity, here's what can go wrong. There's lots of ways to break continuity. There can be, say, a removable discontinuity. There could be, how about a jump discontinuity? But even worse, there could be an infinite discontinuity. Let's put that on paper. There's a vertical asymptote at x equals 2, and the function could do this. It could go upward on that end, and on this end, it could go downward as it heads towards the vertical asymptote. If that's the case, if this is the function we're looking at, well, as far as maximums go, this isn't a maximum right here because the function values get higher and higher and higher. That's not a maximum because, again, there's higher function values here. The same issues about the minimum. There's no minimum here whatsoever because that function value is even lower. And this one's not the absolute minimum because it just gets lower and lower without stopping as well. So this one has no absolute max, nor absolute minimum. It was continuous, or excuse me, it was defined on a closed interval. You know, it's not fully defined, is it? It's missing one spot. F of 2 is undefined. But we can fix that. Here's f of 2. Just put it in a random point anywhere you'd like. You could put it right on the x-axis if you like. That doesn't give a max nor min whatsoever because there's higher values, there's lower values. And now it's defined on the entire closed interval. And so there's no absolute max, no absolute minimum whatsoever on that graph. Lose continuity and weird things like this could happen to the function. And it can get even weirder if we take out the closed interval. In some sense, the closed interval feels just as important as continuity. So here's the new function. Going from 1 to 3, you can make a lot of interesting things happen on this one, but you have to be continuous. So there cannot be a vertical asymptote whatsoever. There can't be any removable holes there, no jump discontinuities or anything like that. But the first issue we have is if it's on an open set, then even if we make the curve go like this, looks like there could be an absolute maximum or an absolute minimum, but that's not true because there's a hole right here on the boundary. There's a hole right here on the boundary on the upper end as well. So this gets higher and higher and higher, but you can't put in an f of 3, it's undefined. This is much like one of those examples, I think the last part of example 1 we were looking into. This is just a different take on that. So this one has no absolute max because of the open hole right here, and it has no absolute min. And we could change the problem. We could make it look like this, for example. It could go like that, jump up really high, jump down really low, and then come back in. And this time it would have an absolute maximum. It's right here. You'd have an absolute minimum way, way down here. But what we're saying is, if we take out the closed interval and make it open, there's no guarantee for an absolute maximum, absolute minimum any longer. It's not that the extreme value theorem was broken. The function was fully continuous, but just not on a closed interval. That interval is open on both ends. So this tells us altogether that continuity and the closed interval are very necessary conditions to getting a guarantee on the absolute maximum and an absolute minimum. Any questions with the graph so far? Okay, now again, we said this is a guarantee for absolute maximum, absolute minimum, as long as you have continuity on a closed domain, so including the endpoints and everything in the middle. So let's put that to a test. The challenge is try to draw a function that's continuous on this interval, closed interval from 1 to 3, and it will have no absolute maximum, no absolute minimum, or one or the other is gone. In that challenge, first thing we have to define is f at 1. We can put it anywhere we want on this vertical strip where the red dot's moving. I'll put it just generically right here. And we also have to define f of 3. You can also put this wherever you'd like. I'll just put it, say, way over here. And now if you're trying to prevent this from being an absolute maximum, the function has to go higher, right? So let's make it go higher. Well, the moment we did that, the absolute maximum just moved to this spot. The absolute minimum is down here. Absolute minimums and maximums can occur right on the boundary point of the domain. But it seems like there's nothing you can do to remove the fact that one value or the other on the outside or in the middle is going to turn into a max or a min. We can't break continuity because we said it's continuous. So when you go to draw the curve, you can make it do something weird, but eventually it's got to go back up to wherever this point was. It has to pass the vertical line test and all those fancy things. So with this next iteration, this is the absolute max. At that height on the y-axis, and this is the absolute minimum at this height on the y-axis as well. So continuity and the closed interval turns into a kind of a magic set of ingredients. And we're going to use these ideas when we're in, say, chapter 5 on integration. We'll later on say a function is integrable provided it's continuous on a closed interval. So these conditions turn out to be really important going beyond maximums and minimums. But that's the extreme value theorem. We're going to take that and use it as a tool when we go into the very end of the notes for finding absolute maximums and absolute minimums, turning it into a process. Next thing we want to look into first is also Fermat's theorem. We're going to combine the extreme value theorem with Fermat's theorem and the observations we made on example 2 about the derivatives being 0 or them not existing in the first place is a good starting point for local mins, local maximums. But any questions whatsoever on this first big theorem? Okay, turning over to Fermat's theorem. We're going to combine Fermat's theorem now with a concept called critical numbers. Sounds kind of important. It's an interesting definition. We'll say a number is a critical number if of a function f, if that number c must be inside the domain of that function, satisfies either the derivative going to 0 or the derivative not existing at all. Critical numbers combined with Fermat's theorem is again telling us these are the first spots we should look for if we're changing from absolute maximums and minimums to local maximums and minimums. That's what we saw happen on the graph in example 2. But there's one big danger when it comes to this. Just because the derivative of f at 0 or doesn't exist, that's no guarantee that you have a maximum or a minimum. You have to look at the functions really close, and that's why in the next chapter, we're going to be looking into something called the first derivative test and the second derivative test. Well, let's make this just a cautious statement here. This is not a guarantee for a max or min It's just the place we start to look. If the derivative is zero in a location, it means we'll look into that location even closer to see if we can determine if it's a minimum or maximum, but it could be neither. And that's what's going on with this function. F of x is x to the power 5/3. It's kind of a strange function. It's the third root, the cubic root of x power 5. It's asking the question, does f have a local maximum or minimum at x equals 0? We're going to take a look at the graph on that to help out, but first, let's find the critical number of this function, just as a warm-up for that concept. Here's what you do to compute a critical number. We need to take a derivative, so we compute f prime to start. So take the derivative of f. That's not so bad because this one's a power function. Power is 5/3. So 5/3 comes down. X is now to the power of 2/3. I subtracted 1 in the form of 3/3 to get the new exponent. So that's step 1. We compute the derivative. Step 2, for looking for a critical number, we're wondering where the derivative does not exist. If that was in the denominator, it wouldn't exist at 0 because we'd be dividing by 0. Aside from that, this derivative is defined everywhere. So instead, we look for where the derivative equals 0. So next step, we just set it to 0 and we solve this equation. That's not so bad. We can multiply by 3/5 on both sides to get x to the power 2/3 equals 0. Then you could take the cube root to both sides, read both sides to powers 2, but the punchline is if x to a power is equal to 0, x is now 0 itself. So that is the critical number of f. So x equals 0 is the critical number of f. And a lot of our methods in section 4.1, 4.2, 4.4, first step of just about everything we do is find this critical number. So we'll be doing a lot of those steps that we just saw here. But now it's asking, is there a local maximum or minimum? This is an unnumbered example because it's not a fair question to where we are so far in the notes. This is something we'll be resolving in the next sections without the use of a graph, but let's treat ourselves to a graph just to see what's going on with this function this one time. Haley says, does that mean x to a power will always have a local maximum minimum at f equals 0? Not necessarily. It's going to depend on the function. Say, for example, if we looked at f of x equals x squared, this one absolutely has a minimum here. But if you change the power to say x cubed, whereas ours is weirder, it's power 5/3. But x cubed is different, right? The function is increasing until it gets to here. It levels off, and the derivative is, in fact, 0 there, but doesn't turn down. It just keeps on increasing from beyond that point. This one has neither a maximum nor a minimum. It just paused in its ascent right at that point. The same issue with the one we're looking at here. This one's to a power 5/3. Really not too different, really. Same exact issue. We know the derivative is 0 when you plug in 0 because that's the whole derivative. Plug 0 here, you get 0 out for f prime of x equals 0. But same issue. As you're going through this graph, it's increasing on the left. You hit the critical number, and then it keeps on increasing. That means that's not a local maximum because values to the right are higher. It's not a local minimum because values to the left are smaller. This one has neither. It's a pretty weird function. Let's put this back on our graph to the right. Oh dear. It disappeared. I'm not sure where it went. There it is. Moving images around on Microsoft's Word is not always the easiest prospect, but there's our function. And yeah, thanks for asking about this one. This is the thing that's kind of surprising. Most of the time when the derivative comes out as 0, And for most functions, well, even functions, even powered functions, we expect a minimum or a maximum, but not in this case. We found a critical number, yet this function has neither a local max nor min at f of 0, or let's just say whatsoever. It's probably the best way to say it. Whatsoever. So that's kind of unfortunate. We've lost the ability to find a maximum or minimum on this one because it never had one to start. So the critical number is a great tool, but the lesson on this particular example is all it's really telling us is it's a place to start looking. It's no guarantee whatsoever for a maximum or a minimum. And this is one of those weird functions. And viewed in terms of what we were saying above here, we had a function that's continuous. X to the power 5/3 is a fully continuous function. We didn't get an absolute maximum or minimum, but that's because the domain of this function is not a closed interval. The domain is r equals -infinity to infinity. If we change the domain on that, we could get an absolute max, an absolute minimum. But in this full domain, we don't have any extreme values whatsoever. Certainly no local maximums, no local minimums. But we're going to see some more tame functions as we go through these notes. And we're going to come back to this concept as well. We'll use this as a way to think about why do we have to run through a first derivative test after we found a critical number. And the reason is, once we find the critical number, we have to actually now go the extra mile and show that critical number led to a maximum or a minimum, that it wasn't this graph that we see right here. Well, next thing we're going to focus on is just getting critical numbers themselves. Then we'll combine it all together on the closed interval method for finding an absolute maximum and an absolute minimum. Just leading off what the extreme value theorem was telling us and using critical numbers all at the same time. So here's our definition for a critical number with a reminder it's not a guarantee for a max or a minimum, but it's a place to start looking. And we have a couple random functions. I'm going to hide part B for the moment so we can focus on part A. All we're doing here is we're finding the critical numbers and then just stopping. So this is just practicing this as a technique. Step one in this process is just differentiate the function. So we go back to the chapter 3 methods. F prime of x, not so bad for this one, it being a polynomial. We get 3x squared minus 6. And then that's our whole derivative. Now, this derivative is a polynomial. That means its domain is all real numbers. So this concept does not apply. The derivative exists everywhere. And usually we're focusing on that concept there. Where is the derivative 0? As 0 will lead to a horizontal tangent line, and in some cases, that will also lead to an absolute maximum minimum or a local maximum minimum. So step 2, we have to solve the following. Solve the derivative of f at x set to 0. So now we're doing equation solving. We'll plug into the left-hand side, 3x squared minus 6 equals 0. And there's a lot of great ways to solve this equation. You could do factoring as a difference of squares. Square root numbers will come up. But x only appears on one term. It's easier to just isolate the x squared. So let's add 6 to both sides. 3x squared is positive 6. Divide by 3. X squared comes out as positive 2. And here's a reminder from days before in algebra. This is a problematic equation because it's quadratic with degree 2. So there's at most 2 solutions for a degree 2 equation. And this one has, in fact, exactly 2 solutions. So if you ever see anything of this form, absolute value, the square root of, well, let's maybe say it this way, slightly different. If you have anything along these lines, x squared equals k, then this will imply that x is equal to negative k or positive k. So in this equation, when we go to take the square root, we get x is positive root 2, or let me follow the order what we did on the right. X is negative root 2, and instead of writing the or, I'll just separate it by a comma. Comma is an official way to say or when we're listing out solutions. So now we have two critical numbers. So say these are the critical numbers of f. So as far as this example went, that's all we were trying to do, look into the critical numbers. We also know interesting things happen when the derivative is 0. Sometimes we have a minimum or a maximum, or like in this case, nothing happens, and it's always kind of shocking. Let's see what happens on this function, just for an extra view on this. Put in the function f of x equals x cubed minus 6x plus 2. And looks like there is a local maximum up here, a local minimum down here. I put in f of negative square root of 2, or rather, yeah, f negative square root 2. The function value for that is 7.65. Now, if you go to square root 2, or negative square root 2, that's about negative 1.41. So go to about that spot, negative 1.41. Here it is. That's the input, negative square root 2, approximated. And notice the output is that function value, f at 7.6568. So this time, the critical number negative root 2 did in fact lead to a maximum. The other critical number down here, here's positive root 2, leads to a local minimum down here. So just because the geometry of the function worked out, the critical numbers actually led to both a minimum and a maximum locally this time. But again, it's never a guarantee. It just depends on the function. If you change this just a little bit, just right, you can make it be something like this on both of the critical numbers. Well, any last thoughts, folks, on getting through this example 3? Okay, let's try it out all over again then. Part B to this process, just the same as before, but this time it's going to require the quotient rule. That's a good review for that. Let's pull this definition down just because it's brand new. So part B, same instructions. All we're looking for are the critical numbers on this one. So step 1 is to just differentiate the function. But this time it's a quotient rule, so we'll write f prime of x, carefully writing it out. No harm to organize, just like we did before. This is going to be an x minus 5 prime times x plus 7 minus x minus 5 times x plus 7 prime. Then divide the whole thing by x plus 7 squared. So there's our quotient rule set up. The derivatives are kind of nice on this one. We're trying not to make the algebra super messy because we're also equation solving at the same time. So the derivative of f at x is going to be a 1 here, multiplying x plus 7. Minus x minus 5 times the other derivative from this spot. This just comes out as a 1. This is all divided by x plus 7 squared. So now when we simplify this a little bit further, we can drop the times 1s, drop the parentheses, and get x plus 7. I said drop the parentheses, but do it carefully on this one. Distribute the negative sign on the inside. Minus x plus 5 all over x plus 7 squared. So the x's cancel, and we have that the derivative of f at x is 12 over x plus 7 to the second power. So that's step one. We compute the derivative, and we definitely want to simplify these as much as feasibly possible, because in step two, we're solving an equation. Step two, solve. The derivative of f at x is 0. Let's take a look at that equation. We're not just solving the derivative of f at x equals 0. We're also wondering, where does the derivative not exist? And that's an interesting thought on this one, because the derivative here does not exist. So dne at x equals -7, because then we've divided by 0. We have a problem with that. So we wonder, is -7 a critical number? This definition is really tricky in a certain sense. Let's read through it again. A critical number of a function f is a number c in the domain of that function f, such that either the derivative is 0 or the derivative does not exist. And there's one number where the derivative does not exist, -7. However, when you look at the original function, -7 is not in the domain in the first place. You can't put -7 there. So this has domain that runs from -infinity up to -7. Union goes from -7 now on off to positive infinity. We just remove one number from the number line, -infinity to positive infinity, in other words. That's the whole domain. And so this one number where the derivative failed to exist, it's not in the domain. So that means it's not even a critical number. So it's a tricky definition because there's a lot more moving parts than we can see usually on the first reading. So here we'll say not in domain. So it's not a critical number. Just kind of an excessively tricky concept on that one. Then it takes us back to the equation solving, but any questions or comments so far with it? Okay, well, here's the next weird concept about this. When we go to solve f prime of x equals 0, we'll always make a substitution right here with what our derivative was, 12 over x plus 7 squared equals 0. But then this automatically, on paper, the way it looks, has no solution whatsoever. Let's think about that as a concept. The reason we can say just by immediate inspection, no solution, is whenever you're solving any structure that looks like this, solving a fraction, a over b equals 0, this always reduces to solving just the numerator set equal to 0. Why is that true? It's because if you're solving this right here, it's a little bit tricky because there's a fraction, but you could just clear the denominator. You can multiply both sides by x plus 7 squared, cancels on the left-hand side. You're feeding that denominator to 0, it just gets annihilated on the right-hand side. It's still 0. So even if we show that step in the middle, let's do it just for the sake of completeness. 12 over x plus 7 squared equals 0. Multiply by x plus 7 squared. Multiply by x plus 7 squared on both sides. Cancellation here. A type of cancellation on the right, 0 just wipes it out. But reduced back to this concept. Solving a fraction set equal to 0 just means take the numerator, whatever it is, set it to 0. So the moment we see that, that's a false equation immediately. There's no variable there. So that means f prime of x equals 0 has no solution There's no critical numbers for where the derivative fails to exist in the domain. And so our conclusion to this is there is no critical number of that function f. This function is weirder than it looks. Usually when we put down a function on paper, we expect to find a critical number, but that's not a guarantee either. There's plenty of functions with none of them, and this is one of them. When we set the derivative to 0 and solve, it reduces to the numerator 12 equals 0, no solution there. When we look for where the derivative failed to exist, there is a number, but that number, -7, is not even in the domain in the first place. So no critical numbers. If we're trying to optimize with this function, looking for maximums and minimums, we just lost our biggest set of tools, making this a pretty tough to work with function. Unless we gave it a closed interval for a domain. The tricky thing is the domain is as large as we can imply, just removing the one bad value. But if we change this function, give it a closed interval, then we can find a maximum and minimum using this method down below. The trouble with this function is the domain is just too broad. It's too unwieldy to work with. And so we couldn't do much with this one. Well, the major concept is, once again, just thinking about critical numbers. And this is a problem where there's just no critical numbers whatsoever for this function. Naomi says, on the earlier problems we did, when we were looking at a theorem, 3, so that's the extreme value theorem, and the graph was continuous at 1, 3. So that's this one right here. Why was the absolute minimum at the part you highlighted at green? You know, that is a great question. It looks like I made a mistake on that one. I thought it would be slightly more to the right. Yeah, absolutely right there. So that was an error on my part. Thanks for spotting that. Let me extend the x-axis down a little bit further. The absolute minimum on this one, my thought is probably I was thinking of a function that went something like this. I know I drew it once, but then I absolutely reverted to this one and did not move. My thought of absolute minimum occurs right around here at this point. So that's the correct and revised absolute minimum. Thanks for pointing that out, Naomi. I was confused as well when I took another look at it. So that's the absolute min there. Other questions at the moment with this graph or other problems we've done? Okay, again, thanks for calling out that error right there. Once these notes are solved, the video ends, the errors are forever. So it's always good to catch these right before we close out for the day. Well, what we'll be doing next when we come back on Tuesday's class next week, we'll do this problem right here, an optimization problem, combining extreme value theorem, our notion on critical numbers, to just write out a process, a kind of algorithm that will absolutely lead to an absolute maximum and minimum each and every time. Extreme value theorem is relevant, so I'm glad you were asking about that one as a refresher, because this is a function that's continuous, provided we're on this closed interval right here. So it will have an absolute maximum minimum, and these will just be the instructions on how to find it. So we'll refresh everything we did when we come back on Tuesday, and then move into the very next section. Well, have a great afternoon, folks. A great weekend. If you have any questions, I'll be happy to help out. Otherwise, we'll be back to it next Tuesday. Thanks. Have a good one. See you later.